You have already noticed that when we create multiple times relatively small data samples with known fixed parameters like mean and standard deviation, each time we get our parameters which are estimated from the data somewhat varying, somewhat jittered. And this is absolutely normal. The same thing you observe when you sample from the real world. You have certain distribution of the data of all the measures possible existing in the nature, and we sample a smaller number of observations because we cannot observe everything. Therefore, sometimes you can sample and by chance see the reality, observe a difference between the zero and the mean, or difference between two means. This doesn't change much the philosophy of what we try to do. But you run your experiment another time, and this time you have bad luck. And you see that your results are not significant anymore. There is always a trend, but trend doesn't count. Your confidence interval is crossing zero line. Therefore, you cannot report that your hypothesis is confirmed. But then you run another experiment and you confirm the results of the first experiment. Luckily, this time, moderately significant. What can we do about this uncertainty in our statistics as a matter of chance? For this, there is a concept and the approach, the method of power analysis. You are already familiar with mean and standard deviation, which can form effect size if you divide mean by standard deviation. Significance level, p less than 0.05, classics, the holy grail of all the researchers. Though for certain domains, this criteria is much more severe, like 0.001 or even stronger. Critical level of significance. The sample size is something that we know, but there is also something which is called power. What's the power? The power is the chance that you don't get your results non-significant given the sample size, significant level, and the effect size. If the effect size is small, which means that the standard deviation is large and the mean difference from zero is small, then the power is less. And those are approximate values of the effect size, which are considered small, moderate, or very important. And now I will try to demonstrate the mechanics, how you can visualize the power of your test. First, we run the first cell to generate some data and to test for significance. So this is 0, and this is the confidence interval. Obviously, it's not crossing 0, so it's significant. We run it again, and we observe that it is significant. We run it another time, it is always significant. So let's make our situation more risky and imagine that we have just 10 samples. Always significantly different from 0. But the interval between the lowest part of the confidence interval and the 0 line varies. Okay, now we can try in an even smaller group, 5. And immediately we get our results non-significant. Another non-significant. The mean is supposed to be the same. The standard deviation is supposed to be the same, but the standard error and subsequently the confidence interval is more extended, which makes the chance of getting negative, non-significant results higher. What we do now, we will try to use this same sample size and a moderate effect size, which is mu divided by sigma. And we run our test with different newly generated data many times, 100 of times. And we plot off the results. And we see how often do we get significant and how often do we get non-significant outcome of the test. That's the result. So what we can see, the power, which is the proportion of the trials which are significant, is 89%, which is pretty high. The conventional power estimate is 80%. 80% chance that we get the significant result if the data is really different from 0. But again, in certain domains, the requirements for the power of the tests are higher. If we reduce the effect size to 0.2, which is the small effect size, which means that we have larger sigma or smaller mean. So in this case it is sigma which is greater. We see that the power is just 29%. So in the most cases, what we observe is not significant. And sometimes it is significant. While the mean is the same, it's just the data which is somehow more variated. Does it mean that the effect is not there? The effect is there, it's always there. But we have less sensitivity for its detection. And the cell 3 is a very nice exercise to see the curve of the dependence between the sample size. This is what we can manipulate. We can make an experiment with 10 samples or with 1,000 of samples. Depends on what is the effect we expect and the critical power we need. So let's imagine that we need a power of 80%. But what is the necessary number of samples? We will progressively increase number of samples, and we run 1,000 tests for each number of samples. Luckily, thanks to our environment, we can easily do it. And we will estimate the power for each sample size from 5 to 100. It takes some time to execute it, but at the end, you will see a beautiful curve. So the power is increasing with increasing the number of samples, while the significance level, the alpha or score is the same, 0.5, and the effect size is fixed at the level of moderate effect size. So for the moderate effect size, where the mean is 2 times less than the sigma, is something like 30 elements, 30 samples. If you need more confidence in detecting your positive results, you can make 40, 42, 45 samples. And if you want to be absolutely sure that you don't miss anything, you do 100 of samples in this experiment. But if your power is stronger, the curve will be different. And it is most likely that you need much less samples. If your power is 0.8, you can be satisfied with just 10 samples. And if you want to be very powerful, you make 40 samples. And there is no reason to increase your sample size any further. So this is what you plan ahead of experiment, ahead of your test. How many samples do you need? How do you know in advance what is your mean, what is your sigma? Based on the literature or based on the pilots, previous experiments from the same lab, the same model. Hopefully, it looks sufficiently simple.